Before we start, that the Fellows Committee is going to meet tomorrow morning at 7, and I believe, in case you weren't aware, Jim Ellen, Elisa Sitovich, Gabi Kotliar, and Peter Littlewood are all on that committee. So I hope you're ready, in principle, to come at 7 tomorrow morning. And let's see, so we have 2 talks left this afternoon. We're stepping away from living matter right now to soft matter, and we'll come back to quantum matter at the end of the session. So this talk is going to be about bent core liquid crystal molecules and confined geometries. As I recall, this was an exchange award between Seoul National, was it, and University of Colorado?
Actually, I'm from Korea.
Right.
I was in Samsung company, and then I quit that company, and I joined the University of Colorado.
Okay.
Yeah.
Very good. All right. Okay. So, and if you could just speak up a little bit for the recording purposes, that would be very helpful. If you need to, you can use this. Use it putting into this microphone here. Thanks very much.
Good evening. I'm going to talk about the bent core of liquid crystal molecules in confined geometry. Actually, I firstly showed some simple and simpler world type or liquid crystal molecules. Then I moved to bent core molecule liquid crystal vision. I guess tomorrow in the morning, the London Hamilton give a great talk about layers, and I'm going to talk about the semantic liquid crystal today. So basically, as you know, the liquid crystal is the intermediate structure between the solid and liquid crystal phase, and it has some somatropic liquid crystal property. As increasing the temperature, you can see the crystallines from crystalline solid to isotropic liquid crystal phase. And I used this kind of simple world type semantic liquid crystals. And as you know, there are many kinds of defects in liquid crystal world, and the representative defect is the photochronic domain, and this kind of onion type, and the other one is this toric photochronic domain, that's called TFCD, and I concentrated on this TFCD. Basically, this is the semantic layers, and that means the molecules are perpendicularly aligned to these layers. This small one is like this. And this is basic idea of the orientation of liquid crystal. Basically, planar alignment of liquid crystal can be achieved on hydrophilic surface like chemically clean glass or some chemically clean wafer. While chromatopically aligned liquid crystal can be obtained on hydrophobic surface such as air. Here, I use the TFCDs on the chemically clean surface. As expected, the molecules on the chemically clean surface, it is aligned parallelly, while this kind of chromatopically aligned molecules obtained in the air. So this is very easy to make. Just dropping sample on the clean glass and wait some time, it can be made like this. And this is simple model for that. As I told you, basically this planar lines molecules on the surface, while this chromatopically aligned molecules in the air. And once this kind of template is formed, if the molecules added this surface, you can get this photochronic domains. But after adding more samples, we cannot see the surface structure anymore because the chromatopically aligned structure in the air is dominant now. And this can be directly investigated by electron microscopy like this. And this is the TFCD. This is well aligned. And with this orange line, we can see the cross-section image. Basically, this liquid crystal is quenched with liquid propane or liquid And we thought about the control of these TFCDs now. So one of the methods is using the confined geometries. Here, I use the silicon microchannels, and the sample is filled like this way. And I use the various kinds of silicon channels from 3 micrometer width to 200 micrometer microchannels. And the very specific width and depth here, depth is 5 micrometer and width is also 5 micrometer. We can get very, very periodic structures in very long range. So, as you can see in this picture, only one toroid TFCDs exist in one channels like this. And this is also directly visualized by scanning electron microscopy. And it was tough because every time I cut the sample, I should throw it out. And it cost much. And with this red section area, as we expected, we can see these tangential aligned structures in it, while the blue section image only shows these planar aligned cement layers in it. And this is simple scheme, and this is model for that. Basically, as I told you in bulk state model, the first layer formed like this, and the molecule loves to parallelly aligned in the surface. So that's why it shows this kind of tangential alignment. And as the molecules are added, it shows the typical TFCD structures. Sometimes, like block polymer work, some polymers transform to different structure by thermal treatment. Here, I use the sublimation process, and once you make this kind of TFCDs, it can be transformed by sublimation. And as time goes on, this normal TFCD goes to this kind of ring-like structures. And this is the result of that. And I guess this is the newest one. And basically, it cannot be achieved by normal formation of liquid crystal. For example, normally, liquid crystal structure can be made from isotopic temperature, and as cooling down, the specific morphology happens. But in this case, we need some pre-made TFCD. And this is also cross-section like this.
I'm sorry, what are we looking at? For instance, on the right there. So the surface there is this layer of cementic, right?
Yes, basically this is skin, and this is normal, and I guess the sublimation happens from the center of the TFCD. So, as you can see in this skin, you can see basically that place was the center of the TFCD.
So what's the positive?
That's the positive.
I understand. Go back to the cartoon. So those donuts, so there's all that stuff, right?
Yeah, these rings, yeah. This ring is made by magnetic materials.
I see.
Yeah, I guess
So
there's
it's nothing deposited. This just grows up out of the
No, this is sublimated and reoriented. I mean, this
supplemented
is
out and reoriented as it comes
right,
up into the surface.
exactly. It's basically, I guess there is some competition between sublimation and reorientation at high temperature. And here I use the 10 micrometer width channel, and as we can see in the 5 micron channel, I mean, that was only one TFCDs in the channel, but here there are a little bit more TFCDs in it. But once the size of TFCDs are fixed from the beginning, I mean, pre-made TFCD exists. I mean, the distance of the originally made TFCDs remain even if we apply some heat. So as you can see in this picture, as time goes on, the distance between the TFCD is not changed. absolutely. And we thought at the time, how can we use this kind of structure in real application? So we thought this could be kind of good microlens arrays. So firstly, we made this TFCD arrays, and with UV curable polymers like NOAA 63, we made replica like this. And by contact microscope printing, we easily made the other replica like this. So we call this TFCD, and this is MMA1 of NOAA 63, and this is MMA2 of DMS. And the structural analysis was done every time we made the replicas. And as you can see in this scanner electron microscopy and AFM images, the original structure was remained.
What's the scale bar size?
Uh,
Is that like 27 microns on the
that is 60 micrometer.
That's 60 microns?
Yes, this is 60 micrometer. That means it is 20 micrometer. But it can be changed with changing the thickness of the film, and it is very easy to control.
But how do you be able to go sub-micron?
Basically, this is kind of feedback of semantic molecules.
I'm sorry, I didn't understand the answer. So when you know, can you create patterns that are sub-micron?
No.
No.
Yeah. So far, it's hard to make. But in the case of the transforming to TFCD, in that case we can make we could make 20 and 200 nanometer cylinders. Yeah. And this is experimental setup. Made the MLAs placed between the liquid lens and kind of projection template. I used the F. So this is the result of the projected image. Basically, input structure of TFCD and MLA2 shows this kind of structure, and this size and the imaging direction can be changed with the depth of focus. Basically, as you can see in normal lens system.
Sorry, I'm not quite following what you're showing there. So these are the insets?
Multiplied and X by MLAs.
I'm sorry?
Basically, I apply some light from here.
Yes.
And this is one net projection template here.
Yeah.
50 millimeter scale. And this is go through MLAs.
Yeah.
And these images are multiplied by these MLAs.
So the insets on the next slide, the insets are the images that you pick up with the microscope?
Yes.
So there's less distortion from the conical. I see. Okay.
Yeah. Dimple, and this is conical. I guess
each of those things is an F.
Yeah.
Yeah, F. The enlarged F.
Each of those dots is an F.
Yeah, each dot.
Oh, each dot is an
F.
F. Wow.
Yeah.
Okay.
It is some multiply.
Now I got it. That's what I didn't get. Thank
I
you.
really think. Now I move to Banco molecule. Basically, this Banco molecules is called as banana molecules because it looks like banana. And it shows the very complex structures. And this is the layer plane. There are 3 layer planes, like polar, silk, and I don't know. Anyway. Basically, it is very switchable materials with electricity and magnetic field, but it is very hard to control the orientation of the molecule structure. But with the confined geometry, we can control the structural orientation. Actually, this picture was selected as liquid crystal beauty in September by the International Liquid Crystal Society. And we are struggling to understand the structure precisely. Based on these optical images, I explain very simply. This bright area is here, the lowest area, like this. And you can see this low position. And this dark area means this high area, high position, like this. And basically, there has not been many studies about the electron microscopy for liquid crystal except some free fracture DM. And DNA liquid crystal can be controlled also by this confined system. Basically, the small DNA molecules can stack end-to-end by end-to-end stack, and with the length of the DNA LC structure, it shows various kinds of structures like this. Especially these structures are also controlled in the combined geometry like this.
5 minutes? Oh,
Yeah.
Perfect. No, 5 minutes, sorry. Give me the signal.
This is
Yeah.
just the property of the chirality of DNA.
Actually, this is about the refractive index and
But
the
if you
omega.
have that chirality, so you have some positional order of the DNA within the channel.
Right, right. I would like to summarize it, and that visualization of TFCD can be done by various imaging techniques, including some electron microscopy and some optical microscopy. And supplemented materials shows ring-like structure. And combined TFCDs shows not only uniform size and periodicity in very long length, and symmetric liquid crystal can be used for imaging applications like microlens array system. And the materials made of identical molecules and DNA liquid crystals can be structurally aligned by general confinement. And I'd like to thank you for collaborating with this, and thank you for inviting me to this great place.
So, questions for Donkey?
So you didn't show scattering. How good are the dots? I mean, how regular is the array?
This one?
Well, or before you had the Fs, right? Yeah, for instance, just when you had the array of holes, or those Fs, if I did scattering, is it very sharp? Are those very sharp? Is that very good regular lattice? If I were using it for, say, template photography, would that work?
Yeah, basically, I was in the semi-conducting business design. So, for the real historical tool, I guess it's hard to be used as a real historical kind of mask. But in this case, it's a little bit bigger than that, and much bigger than that. But it is very simply and fast and thoroughly can be made. So I guess there are other applications.
Yeah, I'm just wondering how regular.
So, if you were to characterize the regularity, how regular is it?
Basically, in the confined geometry, the regularity can be remain near 1 centimeter. But in bulk state, it's hard to say, but a couple of 100 micrometer. Okay. As you can see in this, yeah. If the MLAs are not good, or the regularity is, if the regularity of MLA is bad, we cannot get this kind of clear image. So Here I used a couple of 100 micrometer well-aligned
And I realize I somehow missed, so the periodicity of the lattice you impose or it's self-selected?
It can be changed with depth of focus.
Be changed with what?
Depth of focus.
Right, I understand that, but the initial, say you just have one layer or two layers, the periodicity of your holes, for example, you impose that periodicity or it's self-selected? The defect structure emerges naturally or you impose
Yeah,
it?
naturally.
Yeah.
Yes, definitely. I mean, if some boundary condition is good, the molecules are self-assembled to specific size, the FCD spontaneously.
Right. Okay. Any other questions for Don Ki? Okay, well then, thank you very much. And those are beautiful images and beautiful applications. And we'll move on to the last presentation for today, which is by, we should probably give another round of applause. Which is by Søren, and I'm going to have a hard time pronouncing your last name. But